Hello, everyone. Last week, we talked about requirement classification and organization, and we have also addressed requirement conflict. And finally, we talked about requirements prioritizations and negotiation. This week, we will talk about goal modeling. In particular, we will start with user requirement notations, and then different goal modeling tools, and we will focus on the goal-oriented requirement language, the GRL, with focus on the different notations that can be used to build a goal model, some examples, and how to identify strategies and evaluate a goal model. Let's recall what we have covered in terms of goal modeling from last week. We have identified what is a goal, which is a representation of the stakeholder objectives. In other words, a goal is an objective. We would like to model a goal using goal model, which is a hierarchical arrangement of goals, which actually can be easily demonstrated by identifying the relationships between goals. So a goal model is just a hierarchical representation of all the goals, whether they are soft goals or hard goals. And then we'd like to identify the relationships between those goals to satisfy the objectives of the stakeholders. As we have seen previously, examples of goals could be camera sensor must have 100-degree field of view, and the radar sensor is always on. This is an objective. All sensors must provide reliable data. This is also an objective. Both of these objectives are soft objectives, so we consider them as soft goals. Some of them is related to reliability. Some of them is related to some quantitative assessment, like quality. So we consider them as soft goals. Examples of non-goals: if you would like the software of your camera implementation to be in C, the software implementation for your camera software to be in C language, this is not a soft goal. This is not a goal. The radar housing painted should be in red. This is also not a goal. So what is a goal hierarchy? A goal hierarchy is just a representation of the decomposition of the goals from high-level objectives to low-level objectives. When we say low-level objectives, at the bottom of the hierarchy, or to represent the leaves of the hierarchy. So we do have a hierarchy, and then at the end of the hierarchy, those leaves or those low-level hierarchy will be used to model the requirements. Each goal will be refined with sub-goals that actually define how it can be satisfied. So that the level of satisfaction of each goal depends on the level of satisfaction of each sub-goal. The leaf level goals are considered to be requirements, so we look to them as the low-level goals. As have been stated before, goals could be classified to either hard goals or soft goals. For hard goals, we just call them the functional goals, similar to what we called functional requirements, which more or less related to what the system would perform, like the functionality of the system in terms of an action that the system would perform. For example, vehicles will always stay within lane markings. So this is a function of the system that allow vehicles to stay within the lane markings. It has to be well-defined criteria for satisfaction. On the other hand, non-function goals, which we also call them soft goals, they more or less related to system qualities or reliability as an example. Sometimes we relate to safety. Sometimes we talk about security. So all of these, because it's hard to quantify, we just call them, it's hard to align them to functionality of the system. So we need to quantify them to judge on the quality of a system as an example. Because it's really hard to quantify and even define it, that's why we call it soft goals. An example to this is automatic stop is not jarring to passengers. So we would like to transform this statement, which is a goal for the stakeholder, to be quantified at some point. We're going to use this number to judge on the quality of the goal or the requirement. So that's why we call it is not a function performed by the system. More or less, it's a property or a characteristic or a soft goal that need to be achieved. Let's take the following exercise so we can actually identify the set of goals. Assume you have interviewed the stakeholders, and then you have met with those stakeholders for a certain company. I'm going to call it just X. That is interested to actually design a new autonomous vehicle. And then based on the discussion, their autonomous vehicle system consists of at least 2 sensors. So now we know that in this we have at least 2 sensors. The first one, a camera, and the second one is a radar. Both the camera and the radar are responsible for sensing objects at a minimum distance of at least 10 meters. These sensors can communicate to a CPU via a secure CAN bus, at which point the CPU actually parses the incoming data. For safety purposes, at least one sensor must be active at all times. If you would like to identify the set of goals in the following description, we look to those goals that could be either functional or non-functional goals. So you can see the statement, at least 2 sensors. This is a goal that need to be achieved. We need to use at least 2 sensors. Also, one of the concerns, which we'll translate it later into a goal, is we need to sensing objects with a minimum distance of 10 meters. So that's another goal. Also, we would like the sensors to communicate not with any component, they have to communicate with the CPU. That's another goal. We would like the CPU to parse the incoming data. This is another goal. And finally, one of the quantitative goals is at least one sensor must be active at all time. This is also another goal. So based on this recall discussion, the main principles in goal modeling is all about how you could look to the goal of a stakeholder. The goals of stakeholders are considered as objectives, which a system should actually achieve through a cooperation of actors in the intended software and even in the environment. Where it's your task as a software engineer to model such goals. So we would like to model the goals, especially in the early phases of the project, such that projects may consider how the intended system meets the organizational goals. And even we would like to answer the question related to why the system is needed and how the stakeholders' interests may be addressed. So for a goal model, it is primarily used to express the relationship between the system and its environment. So it's not only on what the system is supposed to do, it's actually about why. So we'd like to model a set of goals in the system, which refers to the objectives of such system, to answer questions related to why. So the understanding would give the reasons of why the system is needed, the context of the system, if it's useful or not. And of course, this is very important because systems are increasingly used to fundamentally change business processes rather than to just automate long-term established practices. Also, a goal model is really important because it clarifies requirements. They are used to specify goals that lead to asking the why questions, and even the how questions and how else questions. Stakeholders' requirements are often revealed in this process with less risk of either missing requirements or over specifying. That means you are trying to ask for things that are not needed. So modeling goals in the early stage of the requirement engineering process is very important. So you guarantee that you will end up with a less risk or a minimum risk of missing any requirements. A goal model is important because it allows large goals to be analyzed into small and realizable goals. So when you build a hierarchy of goals, you more or less like try to split a goal into other sub goals and analyze each sub goal individually. So it really helps into the analysis of large set of goals by breaking those roles into small and realizable set of goals. Also, when you build a good model, it helps on dealing with conflicts because it can identify and help in resolve the trade-offs between cost, as an example, performance, flexibility, security, and even other goals. So if we have multiple goals related to cost, performance, flexibility, security, and there's conflict of satisfying each of those goals, it's easy for us on the early stage of the requirement engineering process to identify the conflicts between those goals through a goal model. Also, it can reveal different, like a different diversion of interest between the stakeholders using such hierarchical representation, and it can also identify conflicts uh, at some point when you go through the hierarchy of the goal model. If you would like to meet one goal which might interfere with meeting another goal, it can be easily extracted and identified in the hierarchy goal graph or goal diagram, which we're going to see later. In a goal model, it helps in completing the set of requirements, as I said before. So the chance of missing requirement is low. At this point, we understand that a goal model is important because it's not only used to identify the entire set or the complete set of requirements, it also used to connect requirements to the design phase. For example, when we study different notations or different language of building a goal model, in particular using the I-STAR notation, which is a commonly used non-functional requirement framework, it uses the goals to guide the design process. So the idea of the I-STAR notation is actually not only to build a goal model to represent the goals and how they are interacting, but also to guide the developers in the design phase. So that being said, goal models are very important. They are used as a nice way of representing or modeling requirements. Not only just a small set of requirements, but it's also a big set of requirements. So it handles lots of goals. It provides different classifications of goals by which you could identify the level of priority of each goal in terms of satisfaction. And it can also help in visualizing the breakdown of each goal into some other sub goals and which one is important to be satisfied and which one is not important to be satisfied. By building such a diagram, we could have a complete vision about the entire set of requirements and how they are interacting, especially if you're going to allocate them at the bottom level of the hierarchy, which I will explain later. And by this, you could easily extract and discover conflicts between requirements. And at the same time, you could identify which requirements are missing and which requirements are not missing. So goal models, to summarize, why do we need goal models? Because it actually provides rationale for the requirements. It identifies stable information in terms of system objectives. It guides requirements elaboration and even the elicitation process because it helps with identifying the complete set of requirements and conflicts in the early stages. In addition, it provides visual representation of the relationship and dependencies between the objectives and the goals. When exactly where we would like to use goal models? So early in the requirement engineering process, as you can see in this graph, this is the requirement engineering stage in the entire software engineering process, after which we will proceed with design and then code and then test. In the first phases of the requirement engineering, in which we are interested to answer the question about why the system is built for. And then in late requirement engineering phase, we will answer questions related to what the system will do. So A goal modeling is very important in the early requirement engineering process to answer questions related to why the system is built for, to identify problems, to explore solutions and alternatives, and even before you build any UML model, you have to build a goal model. So goal models are actually performed prior even to UML modeling, and it is strongly recommended to continue refining the goal models as long as we do have new requirements or even we have obstacles that might be obtained along the requirement engineering cycle. So there are many notations that can be used to model goals based on which methodologies you will employ to model different goals. At the end of the story, the goal model is a hierarchy. How you're going to represent this hierarchy and what's the purpose of the hierarchy will differentiate between different goal modeling techniques. The most common notations or with each technique that is used to model goals is the I star notation, which and its variant, and the goal-oriented requirement language, the GRL, also the COS notations, and of course the UML and case diagrams, use case diagrams. As a matter of fact, in the literature, there are other notations which have been also proposed by various researchers. While the goal structuring notation, the GSN, and even the goal-oriented requirement language are used to make safety cases to satisfy the regularity in even safety-related industry. But there's a lot of work also on using the I-star and the COs and even the UMLs. So in this course, the focus will be on the GRL, the goal-oriented requirement language, which also uses the same notation as the I star. We will focus on this to model goals. So let me give you a summarization of those notations and the differences between each of those methodologies and notations to represent goals. Let me start by goal modeling in the I-START and the goal-oriented requirement language. So the I-STAR goal modeling notations, actually, it helps in providing two kind of diagrams. The first one is called the SD diagram, which stands for strategic dependency diagram, in which we could define relationships between roles in terms of specific goals that one role depends on the other role to provide. And the other diagram is called the SR diagram, which is called strategic rationale diagram, which is used not to define the relationships between the roles. It is used to analyze the goals identified on the SD diagram. So we use the goals from the SD diagram to as an input to the strategic rationale diagram for further analysis into sub goals and even sub tasks. The I-star notations shows each role. We consider a role like could be an actor, it could be an agent, or could be even a position as a large circle. So the representation in diagram would be just a large circle. Inside it, we see goals, tasks, resource, which that role will owns. The ownership in the I-star means that the role desires the satisfaction of its goals, either for its own benefit or actually for the benefit of some other roles or some other actors. Goals may be actually associated with some obstacles. We consider obstacles as negative goals to be aligned or attached to the goals. This is some of the information or characteristics in the I-star modeling. Also, non-functional goals can be modeled as soft goals in the I-star notation. Later on, you will see that the non-functional goals could be actually represented using clouds shape or even indented ovals shape. So if you plan to use the I-star notation or the GRL notation, this is what you would expect. You would expect notations to generate relationships between actors or roles. And also you would expect hierarchy that represent goals and tasks and an actor. And inside an actor, you will see, which is like a big circle in the graph or in the diagram, you will see goals, tasks, and resources. And your task is to identify the relationships between those tasks, agents, and resources and goals, and give more or less like a satisfaction level to each of those tasks and goals, and based on which you will give a satisfaction level for the entire actor. So the difference between actually the goal model in the I-star notation and the GRL language. So although both of them they use the same concepts of an actor, so the same concept of having an actor, and then you have goals or soft goals, and then you have tasks, and you have resources, and you do have the connections or the relationships between goals and sub goals, or like even sub goals connected with each other to, or tasks that are used to make sub goals. At the end, the representation is similar in the I-star and the GRL. However, the I-star framework shares many concepts. The only differences between the two is that in the I-star, it contains many type of actors, not only just an actor. We call the I-star notation as agent-based modeling. So GRU is for goal-based modeling, while most of the notations that use I-star, we call it agent-based modeling. So in the I-star notation, it contains many types of actors like agent, roles, and even positions. And associations or the relationship in the hierarchy will represent either generalization or initiations or covers or occupies or even is part of and plays relationship, in which the GRL does not actually differentiate between those type of relationships. For the links that are defined in either of the two languages, like either the I-star notation or the GRL, there are more restrictions on their usage in the I-star as compared to the GRL. In the I-star, we differentiate between the SD models, in which the focus is on the actors and dependencies, and the SR model, where the internal concern of the actors are defined. In the GRL, on the other hand, it brings in strategies. So we focus on strategies. We could use a combination of qualitative and quantitative contributions. We actually perform actors evaluation, and we even have generic URN links. URN stands for Universal Requirements Notations, and some metadata. What actually we know about the GRL, it makes no distinction between strategic and rational models. Both of them are considered the same, although both views could be expressed in different diagrams of the same GRL model. In GRL, I would share with you a language that is commonly used to build a goal model using the GRL language notation. If you are interested to build a goal model using the I-star notation, the OpenOME tool is really good because it enables the creation and the analysis of the I-star models, especially in the I-star framework. It is commonly used as an interactive implementation. It also uses only forward propagation algorithm with quantitative values, so a little bit advanced if you're interested to look at it. So that the focus will be on the GRL language modeling. It's a variation of the I-star, but a little bit simpler. On the other hand, there are different language notations that can be used to model goals, but using the knowledge acquisition in automated specification. Um, that's called the KAOS or CAOS. So it is a goal-oriented software requirement notation or language, which is used to capture requirement engineering in terms of a visualization or presentation. It is a specific goal modeling method. As compared to the I-STAR, there are some differentiations in terms of representing the actors and the relationships. In the CAUS, it is used to allow requirements to be calculated from goal diagrams, similar to what we did in the I-STAR. The University of Oregon and also the University of Louvain are the initiators of the CAUS method, and this was done in just 1990 by Axel Vaughan and his collaborators. It is very widely used now. It is taught worldwide at different university level to capture and represent the software goals, and we call that, like, at some point, software requirements. The goal modeling using such notation, it provide a way of defining goals and obstacles, and even underpinned by a formal mathematical method of analysis. We will not talk about the cause model in the course. We're just going to focus on the GRL. So as we talked about the GRL and then another notation which is called the cause, the third one is what we have learned and we have seen before, which is the UML. The use case diagrams can actually be used to model goals. It is considered as a simple representation to goal modeling, in which the bubbles would name the functional goals. And we can use the use case diagram forms, would form a simple function only goal model. And use cases cover only the behavior requirements. So this is one of the limitations of the UML, which actually has been provided in the GRL notations, is that in the UML, we focus on functional requirements, while we in the GRL, we focus on both functional and non-functional requirements. In UMLs, the roles are shown as actors, which we have seen before as the stackman, on the diagram linked to the use cases in which they will take part on. And the use cases are drawn as elliptical bubbles representing desired behavior goals. So the focus of the UML just on the behavior goals, which is just the functional goals to represent what the system would do. More interesting is the non-function goals, because the amount of information that would need to be satisfied in non-function goals, it's hard to quantify. So we need more analysis on this type of goals, which can be easily illustrated using the GRL language notation as compared to the UML. That's why it's well recommended to build your goal model using the GRL or even using the I-STAR notation. And then maybe you could align it to some other notations and formulations using the use case diagrams in UMLs. So there are many in the market. There are many goal modeling tools. So the first one, which will be discussed in your lab, and actually we have uploaded a PowerPoint presentation on how to install and download and even try some examples in building goal models using the GUC M Navigator. So which is an Eclipse plugin. Main features of the GRL using this tool, we have 7 GRL evaluation algorithms, and they can be used with color highlight. Also, even you have one model, but you could have multiple diagrams within just one model. References to actors and intentional elements is also included in this tool. It's easily, it is a well-based representation that can be easily used to graph goals and the relationships between such goals. An easy way to actual reference actors and intentional elements is just by drag and drop from the outline or even from the properties menus. It is an auto layout. We also in this tool you will find catalogs, which is used to export and import and even reusing common models. In this language, it is universally used to export graphics, especially BMP and GIF and JPG, and also for exporting strategy evaluation techniques using the CSV file. And it because it uses the GRL commonly notation, which is a subcategory from a notation language to model goals. It also allows the URN links, which is integrated with the UCMs. I will talk about the URNs and the UCMs in the next few slides after the different tools of modeling GRLs notations. So in addition to the UGCM navigator, we also have the Sandrella. The Sandrella, which is a plugin for Visio. So the GUCM navigator is a plugin for like clips. On the other hand, if you familiar with Visio, actually you could use the Sandrella, which is a plugin for Visio, which is also a visualization tool that can be used to model goals and identifying actors, as well as the relationships between goals and the contributions and the satisfaction level of each goal, in addition to the composition of the goals. So it does exactly as the GUC navigator, the juicing, like sometimes we call the GUCM navigator. It also has all the notations for building a goal, for building an actor, for implementing a soft goal, a task, a resource, a belief, and every other contribution levels, as well as links, notations, and the satisfaction level of each goal, which will be discussed in details in the lab, as well as in today's class. A third tool also is called the PyStar, which also available on that website, which is not commonly used as compared to the Sandrella and the JUICEM navigator. But if you're interested, you could give it a try. And finally, we have two more. One of them is called the Creative Leaf. It's a web-based tool. It's not like a software, or it's not a plug-in underneath Eclipse or Visio. It's just like a web-based tool, and it can be found on the following website. And an interesting video on how to use this web-based is also available here. Finally, we do have the Objectifier, which is not used to model goal models using the GRL notation, but rather just using the cause notation. If you're interested to learn more about the cause and how this could be modeled, you might want to give a chance to check this website and see how this tool could be used to model goals, but based on the cause notation. So in the course, the focus will be on the JUICEM navigator tool, and our lab 3 will be designed and implemented using this tool. Now let's start talking about or like give a focus on goal-oriented requirement language, the GRL, how to build the hierarchy, how to identify the components of the hierarchy, how to identify the relationships between the components, and then the major notations that is commonly used to build a goal model using the GRL, and finally how to evaluate such model. When I say evaluate a model, means identify the satisfaction level of each model. And then based on assigning a satisfaction level of each model, you could actually identify the satisfaction level of each actor, which can be easily used later for negotiation between stakeholders. So to actually start the discussion on the GRL, let me go backward a little bit, like one step backward, which is related to the user requirement notation, the URN. The user requirement notation is a big family of notations that focus on early stages of development with either goals or scenario. So if you are interested in building a goal model, you will use the GRL to represent goals, whether they are functional or non-functional requirements. More information about actually a lot of information can be found on the UFT website, where we could identify different information about the GRL, which is summarized in today's class. But if you are interested to study not the goals, rather the scenarios, you could use the use case maps, the UCMs. So it's not only for any scenario, it's more or less related to operational requirements and even the architectures. So combining both the GRL and the UCM is very important to guarantee successful elicitation phase. So the GRL, which uses the I-star notation that I explained earlier, is considered as a modeling language that is used in system development. It is very well known to support goal-oriented modeling and reasoning about goals and requirements, specifically the non-functional requirements. We actually model both functional and non-functionals, non-functional requirements, but actually it is widely used for the purpose of modeling the non-functional requirements. The GRL application and research area, it has been widely used in transformation to message sequence charts and test goals, in addition to architectural evaluations, performance engineering, business process modeling and management, requirement management and policy compliance, pattern formalization, reverse engineering, as well as aspect-oriented requirement engineering. Why do we need GRL? Because goals are an important driver for requirement elaboration. GRL expresses and clarifies tentative, ill-defined, and even ambiguous requirements. It also supports both negotiations, conflict detection, resolution, and decisions, and it even captures decision rationale and criteria related to such rationale, which will be later documented. GRL identifies not only the actors in the goal, the entire goal hierarchy, but also identify alternatives. Those alternatives could be requirements or architectures or other means. The GRL language provides traceability from the strategic objective to the technical requirements. GRL allows reuse for stable higher level goals even when the system is evolving. Keep in mind, it has to be used in the early stages of requirement engineering. It is widely used to model non-functional requirements. That's why it is widely used to model goals, which has all of the previous properties which cannot be seen in the traditional UML language. So GRL in just a nutshell. So if you just would like to describe on the GRL language just in a nutshell, the GRL addresses most of the URN's additional objectives. It is a goal-oriented modeling language in which we understand that the goal-oriented modeling has been proposed in the requirement engineering community for actual number of years, and even several approaches have been published. GRL is rather a new addition to this growing list of techniques, and it also builds on the well-established non-functional requirement framework and even the agent-based oriented I-star notation. Keep in mind that the only difference between the GRL and the I-star is that I-star is used to model agents, while the GL is used to model goals. GRL is a graphical notation for goals, connects requirement to business objectives, allow reasoning about the non-functional requirements, and as I said before, it has roots in the ISTAR and the non-functional requirement framework. It is used to model the why aspects of the platform. It is used to model objectives, alternatives, as well as decision rationales, and even little or no operational details. The GRL supports goal and trade-off analysis and evaluation. On the other hand, the UCM, which is related to scenarios. So in a nutshell, UCMs is also a graphical scenario notation. It is used to represent the causal relationship between responsibilities. In the UCM, the scenario elements may be allocated to components. And it doesn't answer questions related to the why aspects. It answers questions related to the what aspects. That's why the GRLs is used to model goals in the early requirement engineering process, while the UCMs, because we'd like to model scenarios and the responsibilities, it is used to model the scenarios at the later stage of the requirement engineering process. We consider functional requirements in the UCMs as scenarios. Also, we consider integration and reusability of scenarios as part of the UCM model. The guidance for architecture and behavior detail is the main characteristics of the UCMs. UCMs is used not only in performance analysis, but also in conflict detection and transformations. If you would like to connect the GRL and the UCM to identify the relationships between the two, GRL supports the reasoning about the why questions. In particular, it is used to model functional and non-functional requirements. On the other hand, scenarios, the UCMs is used to model as a scenario-based approach that focus on answering questions related to the what question. Keep in mind that goals are breaking down into tasks, like operationally wise, or breaking down into tasks, and tasks are elaborated or even mapped to UCM scenarios. So we start by goals and we end up by scenarios. So when you transform goals into operational tasks and later on into operational scenarios, you are now in the phase of answering the how questions. So you start by the why question, going forward to the what question about what the system will do. So this is why the system is built for, to achieve certain goals. What the system will do, so you more or less look into the scenarios of the system that would help on identifying the functionality of the system. And when you transform goals into tasks and then elaborate those tasks into scenarios at the end, you relate both the why and the what to identify how this is done, especially in the design question, the design phase. Excuse me. So also, combining the GRL and the UCM notations to identify goals and even scenarios, it helps in obtaining a complete and consistent analysis of the requirements. User-defined links for requirement management means that any GRL element can also be linked to any UCM element. So if we are building an actor in a GRL and a scenario and a CUCM, it is easily connected using the notation of both languages. So in GRL, because it's a very good and widely used, and I don't want to say sample because it's not sample, but it's more or less abstract version as compared to the ISTAR, which we have seen before, that it expresses a good way to identify conflicts between goals and even make decisions and resolve such goals, such conflicts. In the GRL diagram, like we are building a GRL diagram to represent given goals in a certain software development process, especially in the requirement phase, there are three main categories of concepts that we see in GRLs. The first one is called intentional elements. The second one is the relationships between those intentional elements and even the actors. Why we call it intentional elements? Because they are used in models that primarily concerned with answering question why, question of requirements. For example, why certain choices for behavior or structure were made, what alternative exists, and what is the reason for choosing such alternatives. That's why it's intentionally designed to answer more about the purpose of the system and how they are linked together. Now let's discuss different notations that are used in the GRL. The first one, as I said, is the intentional elements. Intentional elements could be goals, could be soft goals, could be tasks, could be resource, could be belief, or could be even indicator. What is a goal? In the GRL model, a goal is condition or situation that can be achieved or not to be achieved. A goal is used to define the functional requirement of a system. In GRL notation, it's represented by a rounded rectangle with the goal name inside it. On the other hand, task is used to represent different ways of how to accomplish goal. So what do I need to do in order for me to have this goal achieved? In the GRL notation, task is represented by hexagon with the task name inside it. So this is the representation of tasks. A task is a proposed solution that can achieve a goal and contribute to soft goals and qualities. On the other hand, a soft goal is used to define non-functional requirements. So we use goals to identify functional requirements and soft goal to identify non-functional requirements. It's usually a quality attribute of one of the intentional elements. In the GRL notation, soft goal is represented by a regular curvilinear shape with the soft goal name inside it. So as this shape. A resource is a physical or even informational object that is available for use in the task. Resource is represented in the GRL as a rectangle, like a simple rectangle. Belief is used to represent assumptions and relevant conditions, and this construct is represented as an ellipse in the GRL notation. Finally, indicator is considered as a measure that is used to transform the satisfaction level in the diagram. So now we talked about intentional elements. Now let's move to the second component in goal model represented by GRL notation, which is the relationships. Relationships in the GRL model could be either means ends or decomposition relationship, contribution relationship, or even correlation and dependency relationship. Means ends relationship shows how the goal can be achieved. For example, it can be used to connect a task to a goal. On the other hand, decomposition relationship is used to show the sub components of a task. A contribution relationship describes how one element influences another one. More or less, it's like a weighted means ends relationship, and it could have a positive contribution or a negative contribution value on the connection. So I could see a positive contribution, or I could see just negative contributions. I will show you different type of contributions in a minute. A correlation relationship describe the side effects of existence of one element to another element. And finally, the dependency relationship. So in a dependency relationship, we describe the interdependencies between agents or actors. So to actually draw such links or such relationships between the components, which is like the intentional elements in the goal model represented by the GRL notation, we need to identify for each specific type of links, the notations as well as the meaning of each one. As I said before, it could be a contribution relationship or dependency relationship, decomposition relationships, means ends relationships, or correlation relationship. So in a contribution link, if we do have a contribution link, a contribution would describe the desired impact or even the side effect. As I said before, it could be positive or negative. We could use some qualitative symbols or even quantitative numbers to describe the contributions on those links. So when you see the symbol on the link, that means the contribution is a break contribution. When you see a plus and there's a dot at the top, that means this task is used to make such goal, or this goal is used to make another goal. So more or less it's like a make relationship. If it's just plus, that means we have some positive values added. If it's just minus, we have some negative values added on the contribution link. If it's a dash and then dot underneath it, we call it a hurt relationship. If it's a plus and we have a dot underneath it, we call it a help relationship. If you have plus minus and a question mark, it's called unknown relationship. Each one of those relationships will be weighted in quantitative assessment of the graph. You could use it as it is, and then we're going to call it qualitative. So if you're going to keep the symbols, you will call it qualitative assessment. If you're going to transform it, I'm going to show you later how this could be transformed into numbers. So we're going to do evaluation of the graph using quantitative method. As a matter of fact, there are some alternative techniques that actually use a hybrid method between qualitative symbols and quantitative numbers. So for decomposition links, so if we do have a decomposition link, it is used to define what the intentional element need to be satisfied. What need to do in order for the intentional element to be satisfied, it could be AND decomposition or XOR decomposition. For dependency relationship, we just have like this symbol to show dependency between a source and a target. And the source of the dependency, keep this rule in mind. The source of a dependency relationship cannot be more satisfied than the target. So if the target satisfaction is 100, the source cannot be 120. The source satisfaction level, if I'm going to just use a number to represent satisfaction, if this is 100% satisfaction, this cannot exceed, has to be less than or equal to the 100%. So the source satisfaction in a dependency relationship cannot be more satisfied than the target. Finally, the third component we see it in the GRL notation to model goals is what we called actors. Actors is considered as an active object that actually carries out actions to achieve the goals. In the GRL notation, actors are represented using a circle, and we add the actor name inside it. Agent, on the other hand, is a concrete actor. We can, for example, like human, individual, or even machine, and the role can be taken to be a behavior aspect assigned to either an actor or even an agent. So we might see like just a collapsed actor where everything collapsed inside it, or even we could see an actor like a circle where we have the boundaries, and inside the boundaries we have all the tasks of the goals and all of the intentional elements in the, inside such circle. Actor could be just, it could be an agent, or it could be a generalization form to a role that is used to model the behavior aspects of either the actor or the agent. So if we actually would like to see how an example of an actor that can be modeled using the GRL notation, as you can see here, we have the system actor. So this is the actor, which has several functional goals. So this is a sample for the functional goal. And to achieve such goal, we have two alternatives. So this is task one, which is alternative one that has to be implemented in order to achieve the goal. And then we have another alternative, which is the second task, like option one and option two, that also has to be implemented to achieve the goal. It depends on the decomposition between the two tasks or the two alternatives. If it's or relationship, so one of the alternative is enough. If it's and relationship, means both of the alternatives have to be implemented in order to achieve the goal. So we could have one stakeholder, or we could have multiple stakeholders. So if we have multiple stakeholders, so we have multiple actors. And each stakeholder, they will have their own concerns. At this point, we could model the concerns as soft goals. So here I do have stakeholder A and stakeholder B, and this is just like a component. Here, my actor is just a machine. And as I said before, an actor could be used to model a stakeholder, it could be used to model machines. So multiple stakeholders, they could have multiple goals or they could have multiple concerns. When we call it concern, we're referring to non-functional requirement, which is considered as soft goals. In addition to multiple stakeholders with multiple concerns, actually we might have contributions and even side effects that could provide a way of understanding the relationships between the concerns and which are like the soft goals, concerns and soft goals, and even the goals and the tasks. So as you can see in this graph, option one would have positive impact to concern X, while option two, it has negative contribution to concern X. Option two has positive contribution to concern Y, while option one has negative contribution to concern Y. So you can see that we have some contributions and we might even have some side effects that when you invoke them into the model, you can see potential solutions and impact that connects goals and sub-goals and even the concerns. If we actually expand or zoom in a little bit about what's inside the actor node, I call it like a circle in the diagram, we can see that inside, if we're going to have like expanded actor circle, we could see the entire set of soft goals, we can see tasks, we can see goals, and we can see the relationships, or this is like the side effect relationships and the contributions. We can see decomposition, we can see contribution levels of different notations, and building the circle of the actor could be either collapsed or could be either expanded, in which you identify the actor boundary. Actors could be connected, so it could have an actor as a stakeholder, as I said before, or you could have an actor as a component of the system. If you would like to connect an actor, so if you're interested to connect an actor with another actor, like actor, I'm going to call it electronic accountant, and then another actor called taxpayer, you could connect them based on the dependency through intermediate resources. So you could have a resource element, and then you have a dependency relationship that connects actors with each other. Actually, it could be through resources, or could even could be through goals as well. So this is more like advanced GRL notation that actually allows the notion of understanding the actors in more details. Inside the actor circle, you can see all the goals, hard goals, the soft goals, the tasks, the contributions, and as well as the side effect relationships, or even the correlation relationships and the dependency relationship. So that's more or less like a zoom in of what you would expect to see inside an actor node or a circle in the GRL notation. So when you see this simple, like for example, that's a soft goal. And now we have another two goals, like to satisfy a system security soft goal. It is composed of two other soft goals. The first one is you need to assure the security of the terminal as well as the security of the host. So that's why the decomposition is and relationship. We have two tasks to satisfy the security of terminal. The first task is access authorization task that should be implemented, as well as encryption task. So the contribution of the encryption task, when you see this symbol, it's called make relationship. So that means to achieve the security of the terminal, it is composed of performing two tasks That means we have two alternatives that we need to be done. The two alternatives is accessing authorization, and the other one is encryption. And the impact or the contribution of each of those tasks depends on the contribution value or symbol on the contribution link. There are many different type of contributions. As I said before, it could be a make relationship, a make contribution, a break contribution, adding a help contribution. It could be a positive contribution. It could be equal contribution, unknown contribution, negative contribution, or could be a hurt contribution. When you see this ellipse shape, it refers to a goal. As you can see here, the composition, the decomposition could be either and decomposition, or could be even using or decomposition. So if we have or decomposition means for guaranteeing that authentication is achieved, this goal is achieved, it could be achieved by either the card key or the password or the biometric. That means one of them is enough to guarantee that this goal is satisfied. Also, we could, as I said before, we could see correlation links which show the side effect. It could be a positive side effect, or it could be a plus side effect, or it could be any other side effects that we will see the notations for. We could also have a belief that is connected to a task, and as a matter of fact, it could also be connected to a goal. A practical example related to voice recording system, VRS system. Now we have one actor is called administration leader, another actor is called the system. Inside the administration leader, there are three soft goals that we need to satisfy or achieve. The first one is to minimize the cost. The second goal is to maximize privacy and security. And the third goal is to better use of resources. Also, there is a hard goal which has to be implemented, which is shifting to paperless documentations. And then we have an indicator that is used to align with the soft goal of minimizing the cost, which is the total cost value. On the other hand, in the system actor, we have one goal need to be achieved, which is provide patient information that could be achieved by implementing two alternatives. The first one, either using the VRS voice recording system, or actually could be done on paper. So these are the two alternatives. The relationship between both is just XOR. What's XOR? If this is one, that's a zero. If this is zero, that's a one. That means just one of them to be available at a time. You cannot do both, and you can't have zero. Like it cannot be non-paperless, not without using a paper, not without a VRS. This is not allowed. And it cannot be both. Like I cannot do voice recording system and on paper. It has to be just one of them. So as you can see, there is a connection between the contribution links between actor 1 and actor 2. Like we can see some links connecting the administration leaders and even the system. And those links are used to represent the relationships of goals in terms of different components across different actors. So it's very important to note that we only, not only we have connections inside each actor node or actor circle, but also we can see a lot of connections between different actors based on the communication and the relationships between the actors. So in summarization, we have the GRL notation for the GRL elements and the GRL links and even the satisfaction level. So the goal of building a the objective of building a goal model is to actually prioritize the goals, visualize the goals, understanding which goals should be satisfied, or which goals can be satisfied, and which goals can be fully satisfied, which goals can be denied, which goals can be weakly denied, and which goals can be weakly satisfied, which goals might cause a conflict. As I said, we could actually detect conflicts using the goal model. Which goals I can determine if I will satisfy it or not, and which goals would have like a zero satisfaction, it's non-satisfaction, or even which goals will exceed. the satisfaction. So this notation or these symbols is very important because once you build the goal model, your task is to quantify the model, to come up with a strategy that help in identifying a solution for the models that need to be achieved. So at the end, you would like to use those symbols to quantify the level of satisfaction of each goal, by which you will identify the priority level of each goal given by each stakeholder. Also, on each contribution link, we might see different contribution types. As I said before, it could be a make or a help or some positive contribution, a non-contribution, some negative contribution. It breaks, a node breaks another node, or a goal will break another goal, or this goal might hurt the existence of other goal. This notation is widely used, very important for you to understand the difference between the and decomposition as well as the or composition, especially we are talking about decomposition of tasks into one or more of soft goals or hard goals. So also it's very important to identify the differences between different type of links, either contribution, correlation means and, dependency, or decomposition. We could have just actor with one circle, or could we have actor with boundary, and inside the boundary we can see all the component of the intentional elements. So one example that is commonly used to model goals is using the user stories. For example, using pattern analysis. If we have this pattern in writing the requirements, as an actor, I want to, and then you identify the task. In order to, you identify the contribution to achieve, and then the goal. This user story, it's really good to identify the task of an actor and the contribution level, and even the contribution from the task to a goal, whether it's inside or outside the actor. For example, if I said this is statement when I'm listing requirements, as a professor, so this is the actor, I want to use Brightspace, so this is the task. So use Brightspace would be my task. In order to help, so I'm going to use this symbol, which we have clearly stated before as help. And then the goal at this point would be minimizing. This is a soft goal, the number of lost assignments. So this is how you're going to model the wording of requirements to build a goal model. A common way is the pattern representation. If you have common pattern of actually the listing requirement using the user stories, it's tricky if you have large requirements with different language and with different terminology and different allocation of the words to build the goal model. That's why it's better to be expert in extracting the wording from requirements that identify the goals and tasks and contributions and actors, so you could transform it later to a goal model. Now, with the assumption that we were able to identify the goals from the requirement elicitation document, and then we were able to identify tasks and actors and even contributions, we draw the relationships between the goals, and we draw the relationships between the actors and even the resources. Now it's time to analyze the model. So I could actually make a decision at the end, which strategy I could invoke to guarantee the satisfaction of each goal that I'm interested to satisfy. So that's why goal model analysis is very important. So in goal model analysis, there are two mechanisms that we should focus on. The first one is identifying strategies. And once you identify strategy, you would use it to evaluate the GRL model. Because we know that GRL allows a particular configuration of intentional elements to be defined in a strategy. And what is a strategy? It's just one possible solution in which we will understand and evaluate later the satisfaction level of goals. Strategies is very well used to capture initial and even user-defined satisfaction level for those elements that are separately from the GRL graphs. Keep in mind that wherever you see an intentional element with the star means this is an initial element, especially this commonly used notation in the Jusman Navigator tool. Also, strategies can, which is considered as one possible solution to satisfy each goal, can be compared with each other just for trade-off analysis. So in one goal model, I could have multiple strategies, and those strategies can be used to trade off to come up with a decision which strategy I could invoke it or use it to satisfy the goals of high importance or to satisfy the goals of a given stakeholder. So you could try the strategies to identify and evaluate that your goal model, at which you will determine which strategy is the best to achieve the given goals. So in order to analyze the goal model and even compare solutions with each other, when I say solution means to meet the target of your goals, we need to know which goal has been satisfied and which goal has not been satisfied. We have to evaluate the goal model using evaluation mechanism. The evaluation mechanism depends on a very straightforward strategy, which would propagate the satisfaction level. That means we should have some initial satisfaction level that would need to be propagated to the other elements and even to the actors to show the impact of the proposed solution or the strategy. When I say solution means a strategy, from the low-level goals to the high-level goals of each stakeholders. The propagation will always start by initial values, which is user-defined satisfaction level of intentional elements, and the propagation always start in a bottom-up fashion. So if we have a hierarchy of a goal model, so if we have goals and we have some tasks, and then among those tasks, we might have some composition, we will assign some initial satisfaction level for the task and then propagate it from the bottom up until we find satisfaction level of the high level goal. The satisfaction level of the high level goal is used to find the satisfaction level of the actors or stakeholders. And then you'll see each stakeholder, they have a certain goal. I was successful enough to satisfy the goal of such stakeholders or not, based on the satisfaction level that I can find it by alternating or trying different solutions in my goal models. And once I reach a strategy or a solution that actually provide a concrete answer to the question of, yes, my goals have been satisfied, then you're going to choose the best strategy or the best solution. Evaluation in the GRL language will show the impact of qualitative decisions on the high level soft goals at the top level of the hierarchy. As I said before, the propagation always done in a bottom-up fashion because there is no way to identify hard evaluation. We're always looking for a fuzzy evaluation of the satisfaction level. Keep in mind that in evaluating a goal model, there are 4 parameters that we should consider. The first one is the degree of satisfaction of the children of the tree or the children of the hierarchy. It could be satisfied, it could be denied, or it could be weak satisfied, or it could be weak denied. And this mainly based on a given strategy. So initially, to assess a goal model, you should came up with a strategy and then prove if your strategy is successful or acceptable or not. The second parameter that we also consider is the composition parameter operators. And the third one is the contributions and the correlation and even the dependency relationships. And the fourth one is those importance factors, which is defined for intentional and elements and actors. So we look to satisfaction level, we look to relationship and links, and we look to importance for each component, whether it's an intentional element or even an actor. So one could use numerical values and function instead of qualitative values, which I will especially commonly used in the Jusum Navigator tool, and which will be discussed today. A brief definition of what is a GRL strategy. It is a user-defined set of initial evaluations. It is initially assigned to the leaves of the diagram and propagated to the rest of the model. It is considered as numerical interpretation of the satisfaction level of each goal, and it is implemented using the strategic view. It's really good because it can be easily visualized in a color feedback form. Well, keep in mind that cycles is also allowed. Evaluation of the impact of strategies on the operational and even the architectural aspect using the URN links can easily be extracted if you're going to evaluate each component in the GRL model separately. Strategies in the GUSIM navigator depends always on the initial values. The initial values is denoted in the diagram by the star notation. And then from the initial values, all other values are easily evaluated based on a certain propagation algorithm, as I said before, from bottom up. So as you can see in this example, we have a star. So for the task password, assume now you build your Go model and we have a task called password. And the level of satisfaction is a check mark. This a check mark is a symbol for high level of satisfaction or fully satisfied. So if we're going to quantify this number, it will be 100. If we're going to use a simple star beside it, that means it is initially assigned. On the other hand, and you can see it is colored in green, so you have a dark green means it is fully satisfied. So we can easily assign password. We can easily perform a password task to guarantee that the authentication goal is achieved. On the other hand, if we say the parametric is not satisfied, so the satisfaction level is denied, like you can see this example here. Denied means negative 100. So this is a symbolic value, which is qualitative value. This is a quantitative value. I'm going to show you the table of mapping between a symbolic value and a qualitative value. It would be minus 100, and then if you have a star, means its initial value, user-defined value that we assume it initially and then propagate it in the graph, and then find the final answer at the top of the hierarchy, which is directly connected to the actor. Find a satisfaction factor for the actor, and then make a decision if the solution is what is actually the optimum one or not. So now we have an OR. I'm going to show you later when we have an OR decomposition. OR decomposition would take the max of the two numbers. So we have 100 and negative 100. So the max is 100. So if you guarantee that the password is satisfied, then the authentication also is satisfied with 100% satisfaction. So now let's see how we could evaluate a goal model in the GRL notation. It could be done either qualitative using symbols or quantitative using numbers. Qualitative approach, we always look to the contribution types, which range from the make to break. So we're going to look for the make until the break 1. Or when we refer to the importance of each component, it could be symbolic high, symbolic like H stands for H, symbolic M stands for M, symbolic L, or symbolic N. Also, the qualitative satisfaction level, it could be using a check mark for satisfied, a check mark and then dot means weakly satisfied, a question mark using for unknown, an X and then dot underneath it means weakly desired, and then italic X means denied. So weakly denied or denied, and then conflict using italic Z and then dot for none. These are the symbolic notation for qualitative evaluation. However, we could actually evaluate the goal model using quantitative approach, in which the contribution types will be mapped from those symbolic notion to a number between negative 100 and 100. The importance also will be mapped from high, medium, low, none into a number between 0 and 100. And finally, the qualitative satisfaction level, like those satisfaction levels, also will be mapped to a number between negative 100 and 100. In some research papers and some actual tools, it might be interested to use a hybrid approach where qualitative contribution types are used while quantitative importance is used and quantitative satisfaction levels. If you would like to quantify the GRL qualitative level of satisfaction into numbers, when you see an X symbol, the number is, it's for denied. So this, the goal is denied or cannot be actually achieved with 100% of denial. So it will be assigned a value -100. If you see X and then a dot underneath it, that's weakly denied. So it's any number between 0 and -100. If it's a dot, that means it's undecided, so the value would be 0. If you have a check mark and then there's a dot underneath it, that's a weakly satisfied goal or a task, so it's a number between 0 and 100. And now a check mark will be a fully satisfied um, goal. So that's a value of 100. So in terms of numerical contribution evaluation for the symbols, like the contribution symbols, we could actually convert each contribution level to either a weighted factor, so we look into weights, and then we look to a value of normalization to those weights, or we consider the exact integer number. In most of the GRL notation, we don't use the normalized version. We count on the exact integer number to represent the weight of each contribution symbol. So if you see this symbol, the contribution will be 100%. If you see this symbol, the contribution will be 25. If we see a plus sign, it will be 75. If we see unknown, that's a 0 contribution. If you see the negative sign, that's, we have some negative, which is -75. If we have the break sign, the contribution would be -100. If we have the hurt sign, the contribution would be -25. Those values are used to help on mapping the satisfaction level from the bottom of the tree until the top of the tree to find the full satisfaction level of the final stakeholder, along with its intentional elements. Now let's see how quantitative approach could be used to propagate satisfaction level from a certain level to another level using either the decomposition and the contribution links. As you can see in the following graph, we have and decomposition. So assume I have 3 tasks. The first task is called internet, the second one is called wireless, the third one is called LAN. So connection, to guarantee a connection, it could be done by internet and wireless communication and a LAN. So that's why the decomposition is AND. So in AND, we always consider the minimum for the AND, and for OR, we use the max. So if the contribution of the internet is -50, while the wireless is 80, and the LAN is 0, if you're going to take the minimum of the 3, the minimum will be -50. So this will be the contribution, the satisfaction level of the connection, which is -50. If you're going to do OR, if you're going to, for the OR connection, if we assume that the decomposition between the 3 tasks is just OR, we're going to take the max, which is 80. If you're going to do XOR, which is either or, it's similar to the full satisfaction of one versus the other. So it has to be the one with the max. So we're going to use the 80. So contributions are added but normalized, and keep in mind that sometimes we take the tolerance into account. I'm not going to talk about the tolerance now because that's advanced level. So we're going to talk about the contributions with assume that no tolerance. So there is no tolerance on the graph. So now, as you can see here, we just in the first graph we talked about the decomposition. Here we talk about the contribution links. So this how you're gonna propagate the decompositions from the low level into the high level. And here we would like to see how we're gonna propagate the satisfaction level based on the contribution on the links. So if we have a contribution level, a satisfaction level of -50 for the internet, and the contribution is 50, while for the wireless we have 80, and then the contribution is 100, and then we have for the LAN, the satisfaction level is 0, while the contribution is -50. So this minus, those numbers, in order to find a satisfaction level for this soft goal, it's -50 times 50 plus 100 times 80 minus 50 times 0. So this divided by 100. So we're going to divide all of these by 100. So the value will be the 55. So this is how you propagate the level from from the bottom of the tree into the high level of the tree. And then this really helps on identifying a satisfaction level at the actor level, at the final high level of the tree. So this is the satisfaction level for increasing mobility. So for increasing mobility, it is a number between 0 and 100. So it's weakly satisfied. So it's not fully satisfied. So to emphasize on the decomposition evaluation, as I said before, for the end decomposition, you do the minimum. So if you look to this number, we have soft goal B, another soft goal C, and then C has a level of satisfaction is minus 38, and it's initially given, while this has 75. And then initially given, this one is X underneath dot, and this one is a check mark underneath the dot. So that means this is weakly satisfied, and this is weakly denied. If we're gonna combine them into an AND decomposition, we're gonna take the minimum. So the minimum of the two would be negative 38, and that means it is weakly denied. So the satisfaction level of this soft goal will be X underneath it. Or this is if you're going to use qualitative value. If you're going to use numeric value, it's the minimum of this value will be the minimum of the 75 as well as the negative 38. So it would be the negative 38. On the other hand, if we do our decomposition, we're going to take the max of the two numbers. So if this is weakly satisfied and this is weakly denied, so we're going to take the max, which is 75. So that means this soft goal is weakly satisfied with a level of satisfaction is 75%. So this is for showing that we could actually do and or decomposition based on numeric values. What if we don't have numeric values? We just have symbolic values. So we're going to use qualitative approach. So you can see for AND, we're going to use minimum all the time. And for OR, we're going to use OR all the time. For minimum, if we have weekly denied with like we have three tasks. The first one is weekly denied. The second task is weekly satisfied. And the third task is none. If you're going to end the three tasks together, ending will take the minimum value. The minimum value is weakly denied. So the connection now is the decision for the satisfaction level of the connection goal is weakly denied. If you have fully satisfaction for the internet and fully satisfaction for the wireless and fully satisfaction for the lane, so that means the connection is fully satisfied. If you do have still have three tasks, the first one is weakly denied and the second one is weakly satisfied, while the third one is a conflict. The minimum at this point is considered is conflict because undecided is propagated. In the third example, we do have denied for the internet, and we have weekly satisfied for the wireless, and we have a conflict at this point. The minimum is denied, so we're going to consider denied as the minimum. Even the conflict is present because the conflict is higher as compared to denied, so we're going to take the denied as the final satisfaction level. So if we keep this in mind, if minimum is conflict, so if you do AND decomposition and it turns out that the minimum is conflict at any point, you're going to always propagate unknown. You will not propagate a conflict. You just propagate unknown, and thus you will look backward to relieve and discover such conflict. So if we're going to do the same for the OR notation, where we use qualitative approach, where the assumption that no numbers are given. Now, if we have weakly denied with weakly satisfied and then unknown, if you're going to do the max of the three, so we're going to take the weakly satisfied. If we have weakly denied and weakly denied and also weakly denied, if we're going to do the OR of the three, like just the max of the three, so one of them is just like weakly denied. Here, if also the max is, if we have weakly satisfied and then we have weakly denied and the conflict, so the max here would be considered as a conflict because we cannot propagate conflicts, we will propagate undefined or undecided. The same for if we see the max is in this example, we have weakly denied versus satisfied and then conflict. Even like conflict is present in this example, but we will propagate the max value as a satisfied level. So in we talked about decomposition relationships and we talked about contribution relationships. Now, if we would like to propagate dependency relationship, keep in mind that intentional element evaluation is set to the minimum value in the set of dependency dependency evaluation, or even its current evaluation. So I can, if you can see in this soft goal, it depends on two targets. So we have one source and two targets. The satisfaction level of this soft goal would be just the minimum of the two. So the minimum of a 0 and -30. So it would be -30. So it is weakly denied. So to evaluate an actor, so now we evaluated dependency and we evaluated the decomposition and we even evaluated the contribution. To evaluate an actor, it's important because we'd like to deal with negotiation between stakeholders. You could, after the fact, you have evaluated the satisfaction level of all the components inside your graph. You would like to propagate this upward to find a satisfaction level for your actor such that it helps in the negotiation between the stakeholders. Actor evaluation helps on analyzing and comparing the satisfaction level of each actor based on a given selected strategy, and how this is actually computed based on the importance level of the intentional element references that are bounded to the actors. So in the following example, if we have two actors, actor one and actor two, that here based on the importance level of the soft goal A, where priority is low and criticality is none. And I'm going to show you the graph how you could calculate the importance. So we're going to propagate this to the actor to give a satisfaction level of 25, while for actor two, it is the satisfaction level of 75 because the priority is none and the criticality is high. In most of the questions, you will be provided with just one number, which is called the importance. And the importance could be high or low or medium or even none. So we're going to say none. Where for high, we're going to use a number 100. And for medium, we're going to use a number of 50. And for low, we're going to use 25, while for none is 0. So later on, we're going to replace the priority and criticality by the importance factor. And for a certain actor, if we have actor A, like assume this is the actor A, and it has a lot of soft goals, in each soft goal, this is important high, this is important medium, and this is maybe this importance would be low. How you calculate the satisfaction level of an actor? Simply, you just sum all the contribution, all the satisfaction level. So you take the satisfaction level of each non-intentional element, and then you multiply by the importance level. So you multiply this by the importance level, and then you divide it by this by the sum of importance. And I'm going to show you in the graph how this could be done. So let's take the following example to illustrate the idea of the propagation algorithm that helps in identifying satisfaction level of each goal, which will be used later for negotiation among stakeholders. So based on what strategy or solution you would provide. So as I said, to assess or to evaluate your graph, you have to provide a strategy and then propagate the strategy upwards and then find the satisfaction level of each of your components and then make recommendations. So in this graph, we can see the initial, my strategy, I'm going to call it strategy 1, is I will assume, so initially I'm going to assume the security of host is fully satisfied, and the identification goal is weakly denied, and the biometric is fully satisfied. So you can see that the contribution between the access authorization is a make contribution, and the encryption is a make contribution. The decomposition between the security of terminal, security of host is and decomposition, and the decomposition between authentication and identification also is an and decomposition. The decomposition between card key, password, biometric is an or decomposition. The biometric, they add positive impact to the cost of terminal, while the password adds positive. So the first one, the biometric adds negative impact to the cost of terminal, and the password adds positive impact to the cost of terminal. My strategy, I will assume that's the assumption that the security of host has to be fully satisfied, the identification weakly denied, and the biometric is weakly satisfied. And then I will see when I propagate such a strategy, what kind of a solution, or I will have it at the end, and if this solution is what I'm looking for or not, which means we evaluate the strategy, we evaluate the model based on the given strategy. So as you can see here, if we have the decomposition is OR, so if this is fully satisfied and it's an OR relationship, definitely the authentication is also fully satisfied. And for some reason, those links are not working. Let me try again. Okay, let me try again. Okay, so, and because biometric, they have negative contribution to the cost of terminals. So if this is fully satisfied, it will take it down because it's negative. So we're gonna go from fully satisfied to weakly denied. And then the end decomposition will take the minimum between fully satisfied and weakly denied. So the minimum between the two will be weakly denied. That's the access authorization task. And then this is a make relationship, and this is another make relationship between the access authorization and encryption. So the make relationship is 100% contribution. So we're gonna move forward to find, or if we assume that this is, if we, one missing information here, it should be like this guy should, if we assume initially that this is also weakly satisfied. So if we move upward, this is weakly satisfied and this is weakly satisfied, and the relationship between the two is just make. So this is definitely the security of the terminal is also weakly satisfied, and that means for an entity composition to the upper level in the security system security soft goal, the system soft goal also is weakly satisfied. So if your strategy start with the assumption that encryption is weakly denied, and security of the host is weakly satisfied, and identification is weakly denied, and biometric is fully satisfied, you will end up that the system security is weakly denied. Is this what you want? It depends on the system that you are building. If the system security is high priority, that means the initial strategy that you have initiated is not successful. Now let's try another strategy. For the same goal model, I will try now a different strategy. So if I will assume that password, I'm going to say this is star as initial, is fully satisfied, security of the host is weakly satisfied, and authentication is fully satisfied. So because it's an OR relationship, then the authentication also will be fully satisfied. So, and we have an AND relationship between the authentication and identification. So the access authorization task will be fully satisfied. And because password, they have positive impact on the cost. So the only side effect we might see it is this, it is satisfied, but instead of having weekly denial, as we have seen before, due to the negative contribution, now because of the positive contribution, the fully satisfied will be transformed into weekly satisfied for the cost of terminal soft goal. And now, because we do have and relationship decomposition between the authentication goal and the identification goal. So to have an access authorization, it is fully satisfied because it's an and decomposition. And of course, because we have a make relationship and we assume this is weekly, again, this is weekly denied. I'm going to say this is weekly denied. So a make relationship between the two will guarantee that we are propagating the full satisfaction, like the star and the check mark one. And then because we are taking the minimum between these two in an end decomposition, it should be weekly satisfied at the end. So this strategy, as compared the other strategy ended up with weekly denial, while this one ends up with weekly satisfied. So if system security is of high priority, and then you end up with weekly satisfying this. So strategy 2 is a better solution as compared to strategy 1. So you can see all of our decisions here are done on symbolic notation. There's no numbers at all to propagate it from in the diagram. We just use the symbolic notation and how they can be aggregated or evaluated along the graph from the bottom up, just using the symbols. More interesting if we have actual numbers. Let's take another example where actually instead of only having symbols, we also have level of satisfaction numerically given or quantified, in addition to contribution levels with certain values. And keep in mind, as I said before, whatever you see the symbol star plus, that's a make, so that's 100 contribution. If you see plus and then a dot underneath it, that's a help, which has a 25 contribution. And if you have a plus, this is have some positive contribution, that's 75. And if you have unknown, plus and minus and then question mark, that's a 0. And if you have some negative, that's a negative 75. And if you have a break relationship, that's 1 minus 100. And if you have a hurt contribution, this is a negative 25. So whenever you see a star, it means it is the initial satisfaction level. It is weekly denied. I'm going to use negative 75 as initial given. I'm going to use fully satisfied, which means 100%. Fully satisfied for the security of host. And you can see this actually by the color. Red means a negative value and green means positive value. And the degradation of the color depends on the number between 0 to 100 or negative 100 to a 0. We normally use a yellow color to identify a 0 value, whether it's a level of satisfaction or even a contribution level. So you can see here initially given in this graph, the password is 100% satisfied. The identification is weakly denied by a value of negative 75. The encryption is given with a value of 100%. And the security is initially given with 100%. The 100% value for the security and of host and the 100% for the encryption and the 100% for the password and the negative 70%, this is the strategy. So my strategy will assign 100% for encryption, 100% for security, 100% for the password, and negative 75 for identification. Is this a successful strategy? It depends on the propagation values at the end to determine the satisfaction level. You can see if you propagated this for all relationship, let's do it one step at a time. It's 100, so we're going to take the max. So we still have 100 over here. Now we have an ending relationship between the negative 75 and 100. So propagation would be just negative 75. And now we have a make relationship between the two. So to find the 25 value over here, it's negative 75 times 100, which is because we have a simple make, which has a value of 100 over here. So negative 75 plus 100, and then plus the other one, which is from the encryption components, 100 times 100. And then we divide all of these by 100. So the value will be just 25. And then we, in order to find the 44, we do have the help. So this is the symbol for the help contribution, and this symbol is for some positive. So some positive in the graph here is just a value of 75, and the herb relationship is a value of 25. So if we would like to find the 44, we take the satisfaction level of 25 times some positive, which is 75. And then we add to this the 100 of the security of host times the help contribution, which is 25. And then we divide this by 100. So now the satisfaction level of the system security is 44. It's still positive. So we still have weakly satisfied, which is denoted by the simple check mark and then a dot underneath it. And then if you'd like to find the 33 value, so this 33 will be the 44 from the previous system security soft goal. And then we multiply by the contribution value of the plus, which is the sum value, which is 75. And then we divide this by 100. So this is the value of 33. The same for the 25, it would be the previous value. So this is because we all linked them using the contribution links at this point in this goal. So this is 33 times the contribution value of a plus, which is 75. And then we divide this by 100, so it will be 25. So now it ends up that we have a satisfaction level of 25, which is weakly satisfied. It's still a number between 0 and 100, positive. So to increase sales using the strategy, the initial strategy of 100 encryption, fully satisfied encryption, fully satisfied security of host, and fully satisfied password with weakly denied identification, it ends up that we have weakly satisfied increased sales goal. And to find the satisfaction level of the actor, like we do have the business owner here as an actor, to find the satisfaction level, as I said before, it is calculated as the multiplication of the satisfaction level of each component along with its importance. As you can see here in this graph, we only have few components or intentional elements with just importance. This is high importance. This is high importance, and this is medium importance. So we just have three of components with importance levels. Anything else, if it's not mentioned, then means they have zero, like none, just zero importance. So we don't count them in the satisfaction level calculation of the actors. So to find this business owner, like an actor, satisfaction value, this 42 will be calculated as the 25 of the increased sale because it's high importance. For high importance, we use the value 100. And then we have the system security of high importance. So the system security has a value of 44, and then it's high, so we're going to use 100. And we have the cost of terminal, which has a satisfaction level of 75, which has a medium importance, so that's 50. And then we divide this over the summation of the importance level, 100 plus 100 plus another 50. This will give you the 42. So now we were able to identify that the business owner, that's a stakeholder, we will weakly satisfy his goals. Is this the strategy you're looking for? If the business owner is of high priority, maybe you would like to aim with a higher number. And if the business owner is of low priority, so maybe the 42% is a good satisfaction level. Now, if you change your strategy, no, I'm going to say that I'm going to start by just the security of host is fully satisfied and the identification is still weakly denied. Now I'm not going to use the password as I said before, as we used before. I'm going to use the fingerprint. So the fingerprint is 100% fully satisfied. And I need to find also the business owner contribution based on such a strategy. So my strategy is denoted by the red circles, and maybe you could assume the payment 100% and 100% for the online shopper as well. So if you propagate this bottom up, you will end up that the increased sale now has a value of -17 satisfaction, means it's weakly denied. And it will end up that the business owner is also weakly denied. So the goal of the business owner has weakly denied, like we almost about to deny the goals of such actor. I think with strategy 2, this is not successful strategy because it ends up of denying the goals of the business owner. Now, if we use the third strategy, if I'm going to assume the security of host is 100%, the encryption is 100%, and we still have the 100% payment for the payment and 100% for the online shopper, while we use neutral values or just zero values for the fingerprint and the password and the card key and even the identification. It ends up that increased sales now has a higher level of satisfaction to 51%, and actual the satisfaction level of the business owner has also increased to 52%. So that means that strategy 3 has increased satisfaction level of the business owner. So maybe a strategy 3 is a good solution. So how many strategies I can find? There are many strategies based on which goal you would like to assign initial values for and then propagate it down from the bottom up to find the final value for each actor, which will lead to the stakeholder at the end. And then based on the results, you would make recommendations to choose the best strategy. If the strategy, if the goal is to increase sales and then it ends up that you will not satisfy that such goal, so you would say the strategy is not successful, I'm gonna not use it. But if you choose a certain strategy and this strategy has actually achieved a full satisfaction for the goal that you were aiming for, so the strategy, which is the initial solution to some of the goals, was a good choice of selection. So in summary, we talked about the URN notations, which are actually useful for engineers to specify and even discover requirements. And we talked about goals and scenarios. We even talked about GRL's notations that is commonly used to identify functional and non-functional requirements, and it's efficient to capture goals, objective, and alternatives. And we give like a brief information about the UCMs, which is commonly used for operational requirements and architecture. And it helps in the analysis and transformation of information from scenario and even connected to goals. And it also used for architectural, identify architectural alternatives and dynamic system in the design phase. So thank you for listening, and I'll see you next week.